So let's continue with our lecture series on design for shear and torsion. In this video lecture series on design of reinforced concrete structures, in our previous lecture we looked at the behavior of beams with shear or wave reinforcement, and we will continue that, and we will look at some 2 or 3 different topics today relating to the design for shear. So first we are looking at the design shear strength of concrete in beams. So there are many different factors on which the design shear strength of concrete depends. And those factors may be listed as the grade of concrete, longitudinal reinforcement ratio, shear span to depth ratio, type of aggregate used, size of beam, axial force, and size of coarse aggregate used. So these are the different factors on which the shear strength of concrete depends. And we talked about this shear span to depth ratio also in one of our previous lectures. Out of the many factors on which the design shear strength of concrete depends, this clause 40.2 of our code of practice that we are adopting now, that is IS 456, talks about the design shear strength of concrete. And based on this clause, in table 19 of the same code, we have a table given for design shear strength of concrete. That table I have posted on this slide here, the design shear strength of concrete, tau C, which is given in Newton per millimeter square. And you can see here that among the many factors on which this design shear strength depends, the values given in this table are based primarily on 2 factors. One is the grade of concrete and another is the percentage of longitudinal reinforcement or longitudinal reinforcement ratio. So if you go down this first column here, the percentage or the ratio of longitudinal reinforcement is increasing, and if you go along this row here, you can see different grades of concrete starting with M15 to M40 and above. And these values of design shear strength, which is given in this table here, these are for different values of this PT and concrete grade here. For example, if you want to determine the design shear strength of concrete for a concrete of grade M20 and for the longitudinal reinforcement ratio 0.75, then you can look the corresponding row here and the corresponding column. You can see that the design shear strength of concrete will be 0.56 Newton per millimeter square. So the different values that are given in this table is primarily based on the work of Rangan, which considers the grade of concrete and longitudinal reinforcement. If you want to determine any value here, then you can use this formula here, tau C, which is given by 0.85 times root over 0.8 FCK times root over 1 plus 5 times beta SS minus 1 divided by 6 beta SS, where this beta SS value is either 0.8 FCK divided by 6.89 PT or 1, whichever is greater. So if you look at this formula, you can see that the design shear strength of concrete is dependent on 2 factors here. One is the FCK, which is the characteristic strength of concrete, and another is the longitudinal reinforcement ratio PT. So the table that is given in our code IS 456 is based on this formula here. So this is about the design shear strength of concrete. Next we will see what is the maximum shear stress that can occur in a given beam, or the maximum design shear stress. So let's see here, shear strength of beams cannot be increased beyond a certain limit even with the addition of closely spaced shear reinforcement. It's not that you can install in your beams multiple shear reinforcement or shear stirrups which are spaced very closely apart so that the shear strength of such beams can be increased to a value, whatever value we may need, because when there are large shear forces in the beam, then that will result in the crushing of wave concrete because of the development of compressive stresses. So for any given beam, the value of the shear strength can only be considered up to a certain limit, and beyond that, if the shear forces are high or if we need to resist more shear forces, then you have to either increase the grade of the concrete or you have to increase the depth of your beams. So shear strength of beams cannot be increased beyond a certain limit. And that limit is given in table 20 of IS 456. Table 20, you can find the maximum shear stress, tau C max, this is tau C max, which is given for beams of different grades here from M15, 20, 25, 30, 35 and 40 and above. This value of maximum shear stress is again dependent on or is given by this formula here, 0.631 into root over FCK, and this FCK is the characteristic strength of concrete. So these values are the upper limit on the value of tau C that we got from table 19. So suppose that you are using M20 grade of concrete in your beam, and for that M20 grade from table 20 here, you see that the maximum value of shear stress is 2.8 Newton per millimeter square. But if because of the loads that is coming onto your beam, the value of the shear stress is exceeding 2.8, then you should understand that M20 grade of concrete is now not sufficient. You have to go to a higher grade of concrete. So this is about the maximum shear stress that is allowed in your concrete beams. Now let's see the critical section for shear. Where do you should check in your beam section so that you can find the maximum value of shear force and design for shear according to that value of shear force. So the maximum shear force in a beam usually occurs at the face of the support and reduces progressively away from the support. But when there are concentrated loads, then the shear force remains high in the span between the support and the first concentrated load. That means generally what happens is that the maximum shear force usually occurs at the face of the support. So if you have a beam here that is supported on its end, then this is the face of your support and this is the section where the shear forces are usually the maximum. And if your beam, let's consider a simply supported beam and let us say that there are two concentrated load PP at 1/3 of the length of the beam, that is L by 3 and L by 3. Then in these cases, between this support point and the first concentrated load, the shear forces are usually higher in this case. So if you want to find the critical section for shear, you may look at clause 22.6.2. So what it says is that the shears computed at the face of the support shall be used in the design of the member at that section except as in 22.6.2.1. And what this 22.6.2.1 says is, when the reaction in the direction of the applied shear introduces compression into the end region of the member, sections located at a distance less than d from the face of the support may be designed for the same shear as that computed at distance d. So let me erase this and let me discuss a little about the critical section for shear. So let me draw a diagram here first. Let us suppose that this is a section of the beam. The support is located here. We have some load acting at the top of our beam, some uniformly distributed load. Let us say that this critical section is at a distance of d from the face of the support. We have tensile force acting here due to the presence of longitudinal bars, and the compressive force will act in the compression zone. So generally what happens is, we discussed in our previous lectures also about the presence of inclined shear cracks on our beam. So let us say that this is a section of shear crack. Let me draw it with a different color here. This is a section of shear crack. So what we generally observe is that the closest inclined cracks that I have drawn with a green color here, these closest inclined cracks to the support of the beam will extend upward from the face of the support and reach the compression zone at approximately distance d from the face of the support. So these inclined shear cracks, which originate at the face of the support, they progressively go upwards towards your compression zone of the beam, and they reach the upper part at approximately a distance d from the face of the support. So this is the general nature of shear cracks that we observe in our beams. And in these beams, if we apply load at the top of the beam, that means here, then what is observed is that the stirrups across this crack, these stirrups need only resist the shear force due to the loads acting beyond D. So in these cases, suppose we have some shear reinforcement that is crushing these cracks here. Then in such cases, what is observed is that these shear reinforcement or shear stirrups, they need to resist the shear forces only due to the forces that are acting beyond this section, that is beyond this section which is at a distance d. That means for the loads acting somewhere here in the beam. So what does this mean? This means that the loads applied to the beam between this face of support and the point of this section here, between the face of support and this section here, these are transferred directly to the support by compression in the wave above the crack. So these shear reinforcement, they resist the shear forces due to the loads acting beyond this section A, let's say section AA. So what happens for the loads that are acting above this section? Then these loads are directly transferred to our supports here by compression in the wave above the crack, that is compression in this zone here. So different codes like the American code or ACI code, they permit the design for a maximum factored shear force which is located not at the face of the support but at a distance d from the support. So generally ACI code allows for the design of factored shear which is present at this section here AA, that is at a distance d from the face of the support, and not for the shear that is actually present at the face of the support, because the loads that are present in this side of the beam, they are directly transferred through the compressive stresses in the wave portion of our beam. So this is what we discussed just now, that this is the thing that is stated in this clause here, 22.6.2.1. That means when the reaction in the direction of the applied shear introduces compression into the end region of the member, the sections located at a distance less than d from the face of the support may be designed for the same shear as that computed at distance d. That means for these cases, we can design for the shear forces that is present at a section AA, which is at a distance d from the face of the support. So what are such type of section for which we can calculate for shear forces at section AA? Some examples for these types are given in the figure alongside here. For example, if you see this first figure where the beam is supported on some bearing surface here, then for this type of beam also you can design for the factored shear force which is represented as Vu, and this factored shear force is calculated at a section which is located at a distance d from the face of this bearing support. Also, when your loads are applied at the top of the beam, you may also find some cases in which your beam is inverted and the loads are applied at the bottom of the beam, as in this case here. But when your loads are applied at the top of the beam, for those cases also, you can design for the factored shear force at a distance d from the face of the support. And finally, if you look at this figure C here, if no load is present between the face of the support and up till the section which is at a distance d. No load is present here. For these cases also, you may design for the factored shear force at this place here, which is at a distance of d from the face of the support. So three cases we discussed. First this, second this, and third this. Now let's see other three cases for which you need to design for the shear force exactly at the face of the support. One is this example here, in which the beam is framing into a supporting member in tension. Let's hear what we have said here. This clause cannot be applied in the following situations. That means here this clause refers to this 22.6.2.1. This clause cannot be applied in the following situations. One is the beams framing into a supporting member in tension, which is figure D here. Another is the beam loaded near the bottom, is in the case of inverted beam. This is the case. And finally, for those cases where the concentrated load is introduced within a distance of 2d from the face of the support, is in this left side of the beam here. You can see a concentrated load P is present within a distance of 2d from the face of the support here. So for these cases also you have to consider the factors here at the face of the support. And besides these three figures, if you are designing for corbels or if you are designing for such situations is shown in this diagram here, diagram F. In these cases also you have to consider the factored shear force at the face of the support. So these are the critical section for shear, for where we calculate the factored shear force and design for that amount of shear force. These diagrams are also given in figure 2 in this corresponding clause 22.6.2. Not all these 6 diagrams, but 3 or 4 diagrams are given there. You can check your code also. Now let's look at one last important factor, not so important because you won't be using this enhanced shear strength concept when you are generally designing for dynamic loads or for earthquake loads. This enhanced shear strength is generally taken for beams which are subjected to static loads only. So what is this enhanced shear strength of section? This enhanced shear strength is discussed in clause 40.5 of IS 456. So it has been observed from different tests that shear failures at sections of beams and cantilevers without shear reinforcement, they occur at a plane inclined at an angle of 30 degrees. So if you look at the diagram here, our normal shear failure plane, this generally starts from the face of the support and reaches progressively upwards, making an angle of 30 degrees. So this is the normal failure plane. But when our failure plane is more steep than this, or when our failure plane is inclined more steeply than this, for example, suppose that this is our actual failure plane now instead of the normal failure plane. So for our actual failure plane, which may be inclined at an angle greater than 30 degrees, the shear force required to produce this failure is increased. So in comparison to this shear failure plane, which is inclined at an angle of 30 degrees, if we need shear failure to occur at a plane which is inclined at an angle greater than 30 degrees, for example this failure plane here, then our shear forces should be greater than as compared to this failure plane here. So this generally happens when our shear span to effective depth ratio is less than 2. If you remember one of our previous lectures where we discussed about the behavior of our beams without shear reinforcement, there we looked at a graph comparing the different types of cracks that may appear in our beam based on this shear span to effective depth ratio. This shear span is also depicted in this diagram here. You can see here AV. from the face of the support to the point where our failure plane crosses this upper part of our beam. This is AV or shear span. So this actual failure plane, which is inclined at an angle greater than 30 degrees, they normally occur in a beam with shear span to effective depth ratio greater than 2. As a result of this, we can say that the shear strength of our sections are enhanced close to the supports. So if you see another diagram here which compares tau CE by tau C, here this means the enhanced shear strength of our concrete beam tau CE to the shear strength of concrete tau C with the effective span to shear span to effective depth ratio. You can see that as the shear span to effective depth ratio decreases below 2, from 2 to this line corresponds to AB by D ratio of 0.5. You see that when the shear span to effective depth ratio decreases beyond 2, the shear strength of our sections are greatly enhanced. For example, for this AB by D ratio, our shear strength was equal to the enhanced shear strength. That means the shear strength of our beam was not enhanced in any way, they are equal. But as this ratio decreases, at this value of 0.5, you get the ratio of this enhanced shear strength to normal shear strength to be equal to 4 here. That means now our shear strength is 4 times higher than that of normal shear strength of concrete. So considering this enhanced shear strength, our code of practice, that is our IS code, allows for the enhancement of shear strength near a support. And because of that enhanced shear strength, this clause 40.5.2 also allows for the reduction in the shear reinforcement near the support. Since now we have a greater shear strength, the amount of shear reinforcement needed are also smaller. But generally, this practice is avoided because this reduction in shear reinforcement, or you may say the enhancement of shear strength, that is usually non-conservative for structures subjected to dynamic loads. And also, the reduction in shear reinforcement is not so great that we can achieve a lot of economy. The economy achieved due to the reduction in shear reinforcement is very less. So generally, this reduction in shear reinforcement is achieved, or this reduction in shear reinforcement is done only for cases where our beams are subjected to static loads and not dynamic or earthquake loads. So this is about the enhancement of shear strength. Now we will look at one last topic, and from next lecture onwards we will start with a tutorial class on design for shear forces. And this last topic is the amount of shear reinforcement, maximum and minimum, and the spacing of the stirrups according to our codal provisions. So the minimum shear reinforcement is given in clause 26.5.1.6. Remember, the maximum shear reinforcement is not referred to in our code of practice, but if you search for literatures, then there are also some formula given for the maximum shear reinforcement. But presently we will only talk about the minimum shear reinforcement. This minimum shear reinforcement in the form of stirrups should be provided such that this condition is fulfilled here. ASV, this is the total cross-sectional area of stirrup legs effective in shear divided by BSV, where B is the breadth of the beam and SV is the spacing of stirrup. The ratio of ASB by BSB should be either greater than or equal to 0.4 by 0.87 Fy. So using this condition, you can find the minimum value of shear reinforcement. You can find this ASB value. So here we have Fy on the right hand side. This Fy represents the characteristic strength of the stirrup reinforcement. And remember, our codal provision has restricted the grade of steel to 415 Newton per mm square for shear reinforcement, because higher the grade of steel, there will be rather difficulty in bending of those bars to make stirrups, and also in those bends or in the corner of those bends we may see some brittle failure. So the maximum grade of steel that you can use for shear reinforcement is Fe 415, and you can use this formula to find the minimum shear reinforcement. So these minimum shear reinforcements should be calculated only when the nominal shear stress, tau V, that is the actual shear stress that is developed in your beam, is more than half of the design shear strength of concrete is given in table 19. That means only when tau V is greater than 1 by 2 tau C should you use this minimum shear reinforcement formula, where the maximum shear stress is less than half the permissible value, and in members of minor structural importance such as lintels, this provision need not be complied with. That means you may give some nominal amount of shear reinforcement, and this minimum shear reinforcement provision should not be followed or should not be complied with for these two cases. That is, for case where your nominal shear stress is less than half of permissible value, and for structures of less importance like lintels. So one factor that you need here is the spacing of stirrups. You should decide for the spacing of stirrups using this clause here, 26.5.1.5 of our IS 456 code. And according to this code or this clause, the maximum spacing of shear reinforcement is, if you are using vertical stirrups, then your spacing should be either 0.75D or 300 mm, whichever is smaller. And if you are using inclined stirrups at 45 degree, your spacing of shear reinforcement should be either 1 times D or 300 mm, whichever is smaller. So your spacing of shear reinforcement should not exceed the smaller values of these two, either 0.75D and 300 mm for vertical stirrups, and D or 300 mm for inclined stirrups at 45 degree. So this is about the minimum shear reinforcement area and the spacing of stirrups. So this brings us to the end of today's class. We will start with the design for shear in our next lecture. We will probably have a tutorial class, and then we will move on to the design for torsion. So we'll meet again soon. Till our next lecture, stay safe and thank you.